All right, hello everyone. We will be starting with the session now. Dear authors and invited guests, welcome to Technical Session 2A. My name is Neemahi Patel and this session will be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Conference on Information and Communication Technology for Intelligent Systems, Bangkok, Thailand. The 11th edition of the conference is being organized in a hybrid mode. The physical event will be held tomorrow in Bangkok, Thailand, and the virtual event is being held through Zoom from 9th to 11th April 2026. I hope you will enjoy the knowledgeable and interactive sessions through the day. In this session, we have 10 presentations, and each presenter will be given 10 minutes for presentation and 2 minutes for question and answers. On 9 minutes, I will raise a gentle reminder. There is another request to all the participants that you all stay connected with us till the closing remarks. If you have any query or update, then you can please write it to me in the chat box. Now, before we start with the presentations, I would like to introduce you all to the chair of the session. We have with us Dr. Shikha Sharma. Dr. Shikha is an associate professor and head of department CSE at Purnima University, Jaipur. She is a recognized researcher specializing in machine learning, deep learning, computer vision, and data security, often honored for her academic leadership and contributions to research and patents. A warm welcome to you, ma'am, and I request you to share any introductory remark for our presenters today.
Uh, yes, good morning, everyone present over here. So I feel very honored to be session chair in this prestigious conference. I hope the all the coming presentation would be very insightful, and we all would get some insights from the latest research and all. So all the best for all the participation who will be presenting their paper. Thank you.
Yes, thank you so much. We also have with us Dr. Srinivasalu Gogula. He will be joining us in some time. So we will be starting with the presentations now. I would like to call K. Surya Teja to present his study on adaptive hybrid rhyme optimization for reliable feature selection and photovoltaic MPPT in dynamic conditions. Surya sir, or any of the co-authors present with us? Gauri Prabhakar Sayam. Gauri ma'am, are you here with us?
Yes, ma'am.
Yes, ma'am. Please present your study on AI-driven health risk advisor, a predictive approach to personalized healthcare. Gauri ma'am, are you opening your presentation?
May I audible?
Yes, ma'am.
Okay. Moving to the introduction, a rapid increase in lifestyle
Excuse me,
diseases.
ma'am. We are not able to see your PPT. We can see your list of folders, but not your presentation.
Okay. I don't know why it not sharing.
Could you start your PPT on presentation mode and then share that window on Zoom call?
Okay. Now is visible?
No, ma'am. Please stop your screen share and try again.
Okay.
Ma'am, since we cannot see your PPT still, I request you to please share your recorded version with us.
Okay.
By the time we'll move on to the next person.
Okay, ma'am. Move on to the next person. I will handle the issue.
Yes, ma'am.
Okay.
Now, next, I would like to call Saurabh Nimje. They present a study on breast cancer detection in ultrasound imaging using CLAR and Ensemble Deep Learning, a replication and enhancement study.
Yes, ma'am. Thank you. Just give me 1 second to share my screen. Hope so, ma'am. My screen is visible.
Yes, sir. We can see your PPT. Please start.
Thank you, ma'am. So my paper title is Breast Cancer Reduction in Ultrasonic Imaging using CLAHE and in Ensemble Deep Learning, a replication and enhancement studies. Hello, everyone. I am Saurabh Nimje. Good morning, or sorry, good afternoon to all. I am from DMI HER, Datta Meg Institute of Higher Education, India. These are my contents. So breast cancer is one of the leading cause of death among women worldwide. Early detection significantly improves survival rates and treatment outcomes. Ultrasonic images is widely used due to non-invasive nature, no radiation exposure, and cost-effective also. There is a multiple challenges when ultrasonic images we are captured. First one is low contrast. Second, speckle noise, poor lesson visibility, and need to advance image enhancement and AI-based detection system. So existing approaches. First one is traditional diagnosis method. So there is a mammography and ultrasonic imaging. Second one, machine learning approaches. There is a feature-based classification. Third one, deep learning approaches, CNN-based model and transfer learning model. And fourth one is image enhancement techniques. So histogram, filtering methods, ensemble learning methods. These are the problems in existing approaches. So first one is in ultrasonic images, there is a low image quality affect detection accuracy because of blur and not proper you can say clarity in image. Second one's noise and poor contrast also in ultrasonic image. Third one, single CNN model have limited performance. Fourth one, lack of robustness and generalization. Fifth one, limited interpretability in clinical application. And last one, difficulty in detecting small or unclear lessons. These are my objectives. First one is improve ultrasonic image quality using CLAHER. Second one, develop an assemble CNN model for better classification. Third one, optimize CLAHER parameter for best enhancement. Compare performance with baseline and existing model. And fifth one, achieve high accuracy, sensitive, and specificity. My proposed methodology is, first of all, I collect 200 ultrasonic images where combination of being malmat and normals. So second is this 200 images I convert in multiple we can say scale, angle, and size also. So pre-processing convert image to grayscale and apply CLAHER for contrast enhancement to blur to clear and unclear to clear also. Third steps is feature extraction, where CNN based automatic feature extraction is there. Fourth step, model development. First is baseline CNN. Second, I use a single CNN with CHALER. And third, ensemble CNN with soft volting and weightage averaging. My fifth step, to distribute our training and validation data, training, testing, and validation. So training data, I take 70%, validation 15%, and testing 15%. Data augmentation is used one images converted in multiple 10 or more images. So I take one image using rotation, flipping, and scaling. I convert in 10 images. So 200 images I converted in 2000 images. And sixth and final step is evaluation, where I can calculate accuracies, sensitivity, specificity, precision, F1 score and AUC also. There are the results. So CLAHE, when I use, the image quality is increased. The contrast increase 61.9%, nearly 62%, and edge sharpness is increased 62.9, means 63%. Proposed model performance accuracy is 93.7%, sensitivity 92.5%, specificity 94.5%, and AUC is 0.97%. Here are some key insights. First one, better lensor visibility, improve classification. Second one, enhanceable model, reduce error. And third one, balance dataset, improve reliability. There are the performance comparison, where I can use three models. First means simple CNN, baseline CNN. Second, single CNN. And third one, enhanceable CNN. So I get third, ensemble CNN get high accuracy as compared to other two. So improvement is there in accuracy 8.4%, in F1 score 8.7%, and in AUC 6.6%. These are my conclusions. CLAHER effectively enhance ultrasonic image quality. Second one, ensemble CNN improve classification accuracy and reliability. And proposed model outperform baseline and single CNN model. Fourth one, system is robust, reproducible, and clinically useful. And fifth one, suitable for real world breast cancer diagnosis. Scope of future work are use larger and diverse data set. Second one, integrate explainable AI or XAI for interpretability. And the third one, apply multiple model imaging, ultrasonics plus mammography. These are my references, and thank you to listening my presentation.
Shikha ma'am, any questions for him?
Can you please tell me a little bit about your data set? Which data set you have been used for the breast cancer classification?
So, hello ma'am. So I use ultrasonic dataset. In ultrasonic dataset, one is there is a noise problem, means sometime blur image, sometime not a sharpness image. So using CLAHER, using multiple means computer vision image processing methods or techniques.
So
This
this is the
image
name of your data set. I'm just asking name of your data set.
name is site.
What?
You ask about a site.
Site? I'm just asking name of your data set.
Data set.
You have been taken this data
Ultrasonic
set from
images, ma'am, only.
that I know, sir. I'm not asking which type of content present in your data set. I'm just asking what is the name, because you have downloaded this data set somewhere from the Kaggle or
Yes.
from the open source now. So I'm
Yes,
just
ma'am.
asking what is the name of your data set? How many ultrasound images are present in your data set? I'm just
So,
asking.
ma'am, I have 200 images,
Okay.
ultrasonic images only, and using those images, I enhance means from the 2000 images using scaling, we can say flipping
Augmentation.
and augmentation.
So how did you handle the class imbalance?
Class imbalance. Sorry, ma'am.
Okay, and sir, which particular model you have been used for the ensemble?
CNN plus
Which model of CNN? Any pre-trained model or normal CNN?
normal CNN, ma'am.
Okay. And which strategy, bagging, boosting, stacking, which strategy you have been used for ensemble?
Ma'am, bagging, ma'am.
Bagging. Okay, okay. And can you just let me know, I mean, how practical is your model for the real-time clinical deployment?
So first of all, we take the images, ultrasonic images. Then we enhance that images, and using apply our model, we can predict the tissues of that particular image, where is occur or not. So if tissue is occur, then we can say it is a cancer patient. If it's not occur, then we can say it is a normal patient.
Okay, thank you.
Thank you, ma'am.
Thank you, sir. Next, I would call Naga Sujitha Vumaneni. Sujitha, ma'am. I repeat, Naga, Sujitha, ma'am, or any of the co-authors present with us. All right, Neville Dhinoja. Neville, sir.
Yes, ma'am. I'm present.
Yes, sir. Please present your paper on design principles for regularized meta learning, a framework
Sure.
proposed.
Sure, ma'am. Okay, so is my screen visible, ma'am?
Yes, sir.
Okay, thank you, ma'am. So good evening, panel. Myself, Neville Dinoja, and I'm from Charoswati University. Today presenting the design principle for meta-regularization paper, which is a framework suggestion. Okay, so let's start. If we see, firstly, see what is MML. So MML is nothing but in the real world, where suppose if we say there are rare disease ongoing on during the time of Corona, there were no previous disease existed. So if we consider MML is nothing but it's a few shot learning technique in which we give instead like deep learning we give just few parameters and few data related to the particular problem, and from that we get a proper insight and a proper particular trained model. Okay, so the MML is having the three, we can say three problems which is solved but not inclined properly. So we approach a framework which inclines this model. Okay, so now let's start with the problem. The problem of this vanilla MML is nothing but first is gradient conflict. The task gradients, like in machine learning, oppose each other during the training, canceling out and upgrading, degrading performance. It is suitable, but only for the machine learning or deep learning models where the data is huge. In case of MML, we can't go for the task gradient conflicts. It will not impact the model's accuracy and precision. Okay, so the second problem is optimization instability. So MML loss curve oscillated widely due to competing gradient signals, making the training slow and fragile. And in this kind of scenarios where MML needs proper training, or it's being trained for a particular viral disease or something, so it may be a huge loss, as quoted in the GITELS and FELITELS, the citations 14 and 13. So impact will be unpredictable convergence and sensitive to any hyperparameter change. All right. So the third limitation of this paper of the MML we consider is task prioritization. MML treats every task equally, regardless of difficulty, corrupted labels, or irrelevance. So the impact would be outlier task destabilize meta optimization for all others. So if this will be destabilizing other, then if actually initially we have low data, and if the outliers destabilize the meta optimization like others, so it will be considered as very poor model and with low accuracy and precision of the model. So we have come with the solutions, which is currently the framework proposal. Okay, so our framework integrates three solutions. Each solution target one MML weaknesses as we discussed previously. First, so the first is meta level regularization. Initially, the gradient conflicts which were happening in this phase, the meta level regularization will be solving these problems by implementing random meta and noise injections, L2 parameter regularization, and task distribution coherence. Okay, so this fixes optimization instability, which is in the plain MML and not inclined properly. Okay, the second layer is adaptive optimization, momentum based meta updates, dynamic learning rates, which is dynamic adaptive learning rates, okay, which is a concept of deep learning kind of thing, auto adjust to gradient magnitudes, which flicks the slow convergence. It increases the model speed. The third in framework is task-sensitive gradient management, cosine similarity conflict detection, projection-based conflict resolution, and pre-magnification of normalization, which fixes the gradient conflicts, which was the previous disadvantage of this MML uh, uh, MML problem. The thing is, all the three approaches are separately researched and established and published by our well-known researchers, which are UITEL and Kendall, etc. But the thing is, no one has ever tried to combine this framework and make a integrated single pipeline of these three combined framework. So our framework is trying to do that. Okay. So first solution, the meta-level regularization uh, starts with three things. It introduces meta gradient noise. It injects control noise into meta updates, which triggers the optimization. So when there is overfit minima towards a wild stable genres, towards a wide stable regions that generates across unseen tasks. In here, the precision and the accuracy is very important. There is no chance for false positive or false negative. So this is needed. B, meta parameter L2 regularization. Applied meta initialization, not at task level training. Previously, if we apply the L2 regularization in machine learning or deep learning, it is at task level. In here, we are not computing at the task level, and in MAML, constraint that shares starting point for all task adaptation, preventing extreme parameter value that cause instability. So we are removing instability also in this phase. Third thing is, initially the dynamically downweight outliers and corrupted tasks based on loss derivations. The K, which is implemented in paper, which is theoretically gone there, is controlling sensitivity, preventing destabilized gradient spikes from dominating meta updates. If one is having a proper high bias, then it will be impacting the other parameters also and downgrading the performances. So this was solution one. The two and three or other techniques are adaptive optimization and gradient management. So solution two, in this solution, we are getting the momentum based updates. If we have also heard this term in deep learning also, but we are integrating not we are not inventing something, but we are integrating these things which were initially there as a building structure in our this framework, uh, which is going to be momentum based updates and dynamic learning rates, which updates the momentum and also slows on the large gradient and cures the instability. Third is task sensitive. Okay, so it detects conflicts resolved via projection and magnitude normalization. It normalizes each gradient to unit length, and every task contributes equally, as cited in paper. And the thing is, it removes the component of G that directly opposes GJ, introduces inference. So it resolves the projection in the model. So basically, if we talk about the pipeline, it's a 10 step. Initially, the first three steps are of the vanilla MML, which select task, inner loop adapts, and compute the meta grades. But from the fourth phase itself, we start our pipeline. The fourth phase detects the conflicts. Fifth, project and normalizes the conflicts. Sixth, weight the task. And seven, aggregate the gradients. After these seven phases, the eighth and ninth phases are our solution second and third, which is having L2 plus noise, and ninth, momentum plus adapt LR, which is having the further solution, and which leads us to updated theta value of meta. Okay, so it will repeat until the convergence, until the theta become universal fast adaptation initialization for any new task. So this will be going to work. And so this is our theoretical performance prediction. Projects, the thing is, projection analytically are derived from the component level behaviors in prior literature. We are not pretending this will be the result, but we are getting these things from the previously published paper as a theory concept. Like from Fala et al., it's 13th citation, and G et al., which is 14th citation, accuracy aggregations, and which is 2, 5, and 8 citations. Okay, so now we talk about this is a theoretical upper bound, not a proper indication. It's the empirical is still pending. So we are working on it, that situation. And the thing is, we are using mini method 5A one shot and 5A 5 shot things. So if we are able to achieve the proper accuracy with this model, then we can gain 5 to 10% increase in the previous accuracy as it was, and 20 to 30% fast convergence, 50% less oscillation, and robust gain up to 25%. Okay. Which is based on this literature sources from the previous research paper itself. Okay. Now, so I am open to every questions, ma'am. This is from my side. This is our paper.
Shekha ma'am, any questions?
Yes, sir. Sir, I just want to know why you have chosen the L2 regularization over here.
Ma'am, L2 regulation, because of, if we see, the L2 regulation does nothing but, if we in here I have written, where it's gone. See, we are implementing L2 regulation because we have to regularize the parameter, and if we apply to meta initialization no, we are not introducing at task levels, we are introducing at the meta level. So we have used L2 regularization to regularize the parameter and to prevent the extreme parameter value, which is causing instabilities, to reduce that thing, ma'am.
Okay. Sir, how does your approach prevent the overfitting at both the task level and meta level?
Because, ma'am, if we see the previous papers, they are just implementing a single solution. Suppose they are solving the regularization problem, then they are focusing only on the regularization problem. In this, we are approaching three things at once, ma'am. So it will be for sure reducing overfitting. And as it claims, ma'am, it's a framework proposal. So we are open for every suggestion, continuously improving for our next presentation of this model working itself.
Okay.
Yes, ma'am.
Okay, how would your method perform under the distribution shift?
Sorry, ma'am.
How would your method perform over the distribution shift, or you can say the task heterogeneity?
Okay, ma'am. In this thing, the this thing is, if we talk about this system, we are currently exploring more about this thing. But as per our research till now, we have things that based on our research, the task distribution coherence, which will dynamically down with the outlier and the corruption, and the variable will down variable will cover the sensitivity. So it will prevent destabilizing the gradient spike. As per our research, ma'am, we have learned these things.
Oh, okay, sir. Thank you.
Thank you, ma'am.
Yes, thank you so much, sir. Now, before we move further with the presentations, I would like to introduce Dr. Srinivasalu Gogula, sir, who have joined us as our session chair. Dr. Gogula is a professor and head of department at Vardhaman College of Engineering, Telangana, India. His academic and research work centers on deep learning, natural language processing, machine learning, and data mining. A renowned author and researcher in the field of intelligent systems, he has contributed extensively to advancing modern AI technologies through his publications, mentorship, and leadership in academia. Welcome, sir, and please share a few words with us. Srinivasalu, sir. All right, we'll move on to the presentations then. Lakshmi KS. Ma'am, please present your study on FACE IT, a novel AI framework for preliminary autism screening using facial imaging. Lakshmi KS. Ma'am,
Yes.
are you present?
Yes, ma'am. Am I audible?
Yes, ma'am.
Good morning, everyone. So today I'm going to present my research, that is FACEIT ASD detection using facial images. So these are the contents. Introduction, problem statement, literature survey, methodology, system architecture, module division, implementation, results and discussion, outputs, conclusion, and scope of future work. Autism spectrum disorder refers to a group of complex neurodevelopmental disorders characterized by difficulties in social interaction and repetitive patterns of behavior. So it would be very nice if early identification of the disease can help in the early intervention, and it could potentially improve the quality of life of a person with ASD. Current ASD diagnosis methods are time consuming as well as inaccurate in some cases. So current diagnosis methods for ASD are time consuming. So our aim was to design a tool which can detect ASD from facial images. The diagnostic tool can be self-administered, does not require professional supervision, and returns results much faster without compromising on accuracy. So these were the objectives. The tool should have high accuracy and low time complexity, and real-time capture and diagnosis of subjects is possible, capturing uncertainty within the data. And early diagnosis can help in early intervention. And this method could possibly be extended for use in diagnosis of other diseases such as ADHD. Then the main challenge in this work is we are not having publicly available data set for ASD. So we have collected data from nearby hospitals around Kochi, and we got only 314 samples related to autism spectrum disorder, and we have worked on it. And these were the some of the papers related to autism detection in the earlier works, but most of them were using machine learning techniques, and the accuracy was also not really promising. So in our work, we have used Bayesian CNN, and Bayesian CNN is a probabilistic neural network that outputs a probability value for each of the possible classes. So instead of using convolutional neural network, we have used Bayesian CNN, which gives an uncertainty also along with the possibility of ASD prediction. And weights are considered as distributions with a specific mean and standard deviation rather than using just a value. So it works based on a method called Bayes by backpropagation. So this shows the difference between Bayesian CNN and normal CNN. So we can see that instead of using the actual weights for connecting different layers, the distribution is used instead of using the actual weights in Bayesian CNN. And for giving explainability to the model, LIME was used. LIME stands for Local Interpretable Model Agnostic Explanation. So it is an explainable AI method which can give explanations for almost any model by treating it as a black box. So it produces explanations for a single sample or observation. And it produces a subset of images which will be perturbed and use the model to classify these images. And the perturbed parts of the image are used to identify the importance of the part in the classification of the actual image. So this shows the system architecture. First, the images have been uploaded and then converted into pixel values, and the basic pre-processing steps were done. And it is given to Bayesian CNN model. And from that, we have produced the line explanation. So this is the Bayesian CNN architecture for ASD detection. 3 layers of convolutional layer have Bayesian probabilistic convolutional layer has been used. And these are the steps: dataset identification, data pre-processing, then use of Bayesian CNN, then line for model explanation, then web app and model integration followed by interface finalization. And these were the hardwares used. And we have developed it using Jupyter Notebook. And the accuracy obtained is around 85%. And the precision and recall F1 score specificity value all are shown here. So high precision indicates there were low false positives, and good recall shows effective detection of ASD cases, and high specificity ensures correct identification of non-ASD individuals. And these are the normal distribution training laws and Bernoulli distribution training laws. normal distribution training accuracy and Bernoulli distribution training accuracy. This is a validation accuracy. So we can see that the model performs well. So this is the output using the web app interface developed. So here we can upload the image and line explanation. The parts indicated in green line shows the region where the region that is used for detecting the ASD. So we have successfully implemented Bayesian CNN for detecting ASD from facial images, developed an interface for user to conveniently test for ASD without much time complexity or supervision, and implemented LIME to generate explanations for single instance classifications. These are the scope for future improvements. It can be applied for ADHD. Then expansion of model capabilities could enhance its application and impact in the medical field. That's all about the presentation. Thank you. Now I'm free to open for the questions.
Come on, any
Yes.
questions for him? Her?
Yes, ma'am. Ma'am, first and foremost, important question, can the facial imaging alone be sufficient to handle the autism screening?
Ma'am, it can be used as an initial stage for screening autism. It alone cannot be used for giving 100% accuracy, but for an initial screening process, it can be used.
Yeah, because there could be a number of methods to handle the autisms, you know.
Yes, ma'am.
So only the facial images is not only responsible to detect the autism, even on the initial stages. Okay, can you just let me know how does your model handle the broader line or the ambiguous cases?
It was able to detect most of the, it has given accuracy around 85%, ma'am.
I'm asking how they handle the borderline or ambiguous cases.
Or just a minute.
Okay, ma'am. Thank you.
Okay.
Srinivasanu sir, any questions for ma'am?
Okay, sir. Fine, madam. All questions were clear.
Okay, thank you so much. Thank you, ma'am.
Thank you.
Now, next, I would like to call Nabila Kausar to present a study on feature fusion-based enhanced information representation for improved accuracy of BCRP inhibition prediction in drug discovery. Nabila ma'am or any of the co-authors? All right, Naga Sujita Vumaneni.
Hi.
Naga Sujita ma'am.
Hi.
Hi ma'am,
I
please
am
present your paper on full stack tiny ML for scalable IoT sensing, a quantitative study of quantization, sparsity, and compiler runtime co-design in microcontrollers.
Are you able to see my screen?
Yes, ma'am.
Thank you. Good morning or good afternoon, everyone. So this paper takes TinyML beyond small model interface into a full stack system discipline. We study how model architecture quantization, sparfication, compiler transformations, kernel libraries, and memory planning interact to determine whether a deployment meets hard MCU constraints. So the key finding here is the training how we have done and how robust we have got the results, and also the unstructured sparsity, what it saves the flash but not the latency. So we will dig into that. Now, we have four reasons why TinyML on microcontrollers is essential for IoT. So first one would be the bandwidth cost, which makes the streamlining raw sensor data prohibitive at scale. And the second one would be the tile latency from cloud round trips, which breaks the real-time detection. And the third one would be the privacy, which requires keeping sensitive sensor data local. And the last one would be the energy budgets that demand transmitting interferences like bytes rather than the raw kilo data, the kilobytes. The TinyML is a full stack discipline with six interacting layers. So the model architecture sets the theoretical compute budget. Quantization determines actual precision and memory cost. Sparsity removes parameters but may not help latency without kernel support. So the compiler translates the model graph into instructions. The graph fusion reduces the activation traffic. Kernel libraries determine hardware utilization, and memory planning determines if the model fits in SRAM at all. So these three layers interact. A quantization choice that saves compute may increase activation size if the compiler cannot fuse operators. So our study quantifies these interactions. We studied three representative IoT workloads. The keyword spotting uses DSCNN classifier over MFCC features. The canonical TinyML benchmark anomaly detection uses autoencoders for industrial predictive maintenance. The image classification uses a small mobile net for visual inspection. So each has different model sizes and activation memory requirements, creating different constraints on the MCU. So the KWS is the easiest fit. Image classification pushes SRAM limits on smaller MCUs. Interference latency decomposes into three components. So the T compute scales with MACs divided by effective throughput. This is what the quantization reduces. The T memory scales with the activation bytes divided by SRAM bandwidth. This dominates on memory bound MCUs. T runtime captures operator dispatch and format conversion overhead. So this is what the compiler graph fusion reduces. So the energy has a similar decomposition. Compute energy, SRAM access energy, flash read energy, and overtime overhead. So all has a similar comparison. Understanding which component dominates for our workload determines which optimization to prioritize. The quantization comparison makes the case clearly. So that is 2.5x speed up and 3.8x flash reduction and less than 0.2% accuracy loss. Int4 pushes further but requires quantization aware training and loses 2.1% accuracy. So the binary quantization saves the most but loses 7.7% accuracy. For most deployments per channel, int8 PTQ is the clear winner. Best accuracy efficiency trade-off with minimal effort. Unstructured sparsity is primarily a flash optimization. So the reason here is like without sparse kernel support on the target MCU, the pruned weights are stored on dense tensors with zeros. So the MCU still process them. The structured sparsity here does reduce latency because it actually changes the model architecture, removing entire channels that reduces both computation and memory, but this requires retaining. The compiler and runtime stack provides massive gains without changing the model. Here, all without changing a single model parameter, we can have the TinyML full stack discipline. So here we can see the 5 deployment rules. So the rule 1 would be the start with int8 per channel PTQ. Rule 2 would be use CMSIS NN optimized kernels. And rule 3 would be enable compiler graph fusion. Rule 4 is budget SRAM first. Check memory fit before optimizing latency. Rule 5 is prefer structured over unstructured sparsity. Only structured pruning actually reduces the interface timeline. 4 takeaways here. Int 8 PTQ is robust by default. Optimized kernel libraries are the single biggest lever. The compiler graph fusion is free performance, and unstructured sparsity saves flash, not latency. So here the closing message would be the TinyML is a full stack discipline which optimizes the system, not just the model. Thank you, and happy to take any questions.
Jika ma'am, any questions?
Yes, ma'am. Just a minute, ma'am. Ma'am, can you just let me know what is the key novelty compared to existing TinyML pipeline?
So the existing TinyML pipeline, there were like multiple researches that has been done, but I don't think so. Like most of the research doesn't focus on the multiple sparsities what we have done, and also the data set that we have taken is with the vast majority of the use cases compared with the existing research.
Okay, ma'am, can you just let me know how scalable is your approach for the large IoT networks?
I think with our testing, we went up till whatever the capacity of the use cases that we have to test. But in the real world scenarios, I'm not sure about that number of the scalability.
Okay, thank you, thank you.
And just one question. I think my previous ChatGPT paper had to be spoken, but I think I'm in PST's time zone and I misinterpreted the time. So can I please present that paper?
Yes, ma'am. Actually, you have three papers, correct?
Yes.
So after this, you can present your Raspberry paper, and then I would request you to present your ChatGPT paper as well.
Okay. Can I go ahead and present the Raspberry paper?
Yes, ma'am. Please wait a second. Srinivasanu, sir, any questions for ma'am for this paper?
Madam, have you practically applying these technicals anywhere?
I think the TinyML IoT has been researching in a lot of different perspectives.
No. In your paper, have you tested elsewhere?
We have tested with the sample data sets, but not with the real world.
What is the size of data set, madam?
I think so. What we have used is about 15,000 samples on each use cases, and we have used like about 5 use cases.
This is synthesis data.
I think so. So my co-author has done the data curation part.
Okay. Only thing with the synthesis data, probably all the results will be biased. Better to generate or take the real-time data set and test it again.
Okay, sure.
Thank you.
Yes, thank you, ma'am. Now, next, please present your paper on Raspberry Pi centric IoT in 2024 to 26, a quantitative study of edge gateway scaling, containerized microservices, and on device AI.
Okay, sure. Give me 1 second. Are you able to see my screen?
Yes, ma'am.
Okay, cool. Yeah, so this paper presents a quantitative study of Raspberry Pi centric IoT. So the Pi 5 with the Cortex A76 CPU and RP1 input IO controller has evolved from an educational device into a credible edge platform. So we study three trends here: the gateway scaling under growing device populations, containerized microservices with K3s, and on-device AI with TensorFlow Lite. So we develop analytical models for latency and energy. We test four hypotheses about scaling behavior and derive actionable design rules for capacity planning. So the Raspberry Pi SBCs have four key advantages for IoT edge computing. So the low cost makes them accessible for large scale deployments. So the full Linux compatibility means you can run containers, databases, and ML frameworks natively. So the rich input IO connects to any sensor ecosystem, and the growing software ecosystem brings cloud native patterns to the edge. So the central engineering question here is, when does a Pi gateway remain deadline feasible and energy efficient as devices sampling rates and gateway services increase? So this is a capacity planning problem with a strong non-linearities. So here the Pi 5 represents a significant problem shift. So the platform shift. So the Cortex A76 CPU delivers a 60% more instructions per clock than the A72. The dedicated RP1 IO controller separates peripheral management with the main CPU. Here, the Debian 12 bookworm provides native 64-bit support. K3s brings certified Kubernetes to the edge, and the TensorFlow Lite with int 8 quantization delivers 2 to 3x faster interference than FP32 CPU only. And here we structure the study around four testable hypotheses. So H1 predicts a sharp latency knee from M1 queuing. H2 predicts convex energy behavior favoring partial offload. So H3 predicts super linear throughput, degradation from container interference. So H4 predicts int 8 quantization shifts that the feasibility knee has. So all four were validated by our simulations. So here the gateway pipeline shows a sensor sending the data via radio uplink to the Pi 5 gateway, which performs verification interference and aggregation before forwarding to the cloud storage and operation dashboards. So the latency decomposes into sensing transmission, queuing, and the queuing interference and aggregation. So here the energy combines radio transmission cost and compute cost. We studied three workload classes of increasing complexity. W1 is lightweight secure aggregation, W2 adds edge interference filtering, and W3 adds multiple containerized microservices. Each creates different load on the gateway. The latency knee is dramatic. At utilization 0.7, latency is comfortable, which is 35 ms with a 2% miss rate. At 0.85, it rises to 85 milliseconds with 15% misses, which is the warning zone. Just 7% points higher at the 0.92, the latency explodes to 210 milliseconds with 52% misses. At 0.98, the system has essentially failed at 850 milliseconds and 95% misses. So the key operational insight here is a 5% utilization increase from 0.85 to 0.92 causes a 2.5x latency spike and a 37% point jump in miss rate. So this is the capacity planning signal. When utilization exceeds 0.7 to 0.8, start planning to add gateways to reduce sampling rates. The energy offload trade-off is convex. So at r equal to 0, all edge, radio energy is low, but compute energy is high. Total is 50 mJ. At r equal to 1, all cloud, radio energy is very high, but compute is minimal, still 50 mJ. The minimum is at r star equal approximately equal to 0.3 with the total energy of 33 mJ. Um, a 34% savings over either extreme. The optimal offload ratio depends on link budget and interference cost. For Pi 5 with a typical Wi-Fi, partial edge processing with cloud fallback is almost always the best. H3 container interference is the throughput that degrades superlinearly. Three containers cause 18% degradation, five containers cause 39%, eight containers cause 62%, meaning the gateway delivers less than 40% of its single container throughput. H4 quantization benefit is that int 8 provides consistent 2.4 to 2.5x speed across the model architectures. Mobile net drops from 45 milliseconds to 18 milliseconds. DSCNN were from 22 milliseconds to 9 milliseconds. So this can convert an infeasible configuration into a feasible one without changing the hardware. So the practical implication here is budget the containers count carefully and always quantize for edge AI. So here we follow 5 design rules for Raspberry Pi IoT capacity planning. Rule 1 is monitor utilization, add gateways when it exceeds 0.7. Rule 2 is use partial offload at R star approximately equal to 0.3 for minimum energy. And rule 3 is always quantize to int 8, free 2.4x speed up. Rule 4 is budget container count. Each one adds superlinear overhead. Rule 5 is start simple with aggregation, add interference only if bandwidth savings justify it. So finally here the Raspberry Pi SBCs have become a credible IoT edge gateways. Four key findings here. The sharp latency means monitor utilization as your capacity signal. Convex energy favors partial offload. Int 8 quantization is essentially free performance, and container count must be budgeted carefully. Thank you, and I'm open for questions.
Yes, Shikha ma'am, any questions?
Yes, ma'am. Just give me a moment. I just a minute. Ma'am, can you just let me know, ma'am, why you have chosen the Raspberry Pi as a central platform?
I think actually like we tried multiple research patterns, but like we found this as best fit under when we simulated with the with these 5 rules. We thought Raspberry Pi would have been best fit compared to the other IoT models.
Okay. Ma'am, can you just let me know how you handle the authentication and secure communication part?
Um, so we didn't dig much depth in the security perspective.
Okay, ma'am. Okay.
All right, Srinivasanu sir, any questions?
Fine, madam. No questions.
All right. Yes, ma'am. Naga ma'am, please present your study on ChatGPT enabled IoT at the edge. a quantitative study of latency, energy, and security under latest LLM trends.
Thank you. Can you see my screen?
Yes, ma'am.
So this paper addresses how ChatGPT and LLM capabilities should be integrated into IoT systems without breaking latency budgets, increasing the energy costs, or introducing security vulnerabilities through RAG pipelines. So here we have dig into like a little bit of security vulnerabilities and all for your previous question, ma'am, Shika, ma'am. We develop a stage-wise analytical model for end-to-end latency and energy, propose a trust-aware RAG guardrail, and compare four architectures from cloud-centric to on-device. So the key finding here would be the cloud-centric designs violate a 150 milliseconds interactive budget at modest scale. So while hybrid semantic compression and on-device small LLMs maintain lower tail latency and reduce per request energy by 4.4x. So this is a quantitative simulation driven study with reproducible parameters that sweeps and actionable deployments threshold. So why this matters, right? So the IoT operators increasingly demand conversational interactions, summarizing anomalies, diagnosing equipment issues, planning firmware updates. LLMs like ChatGPT can synthesize telemetry, translate logs into hypotheses, and draft checklists. So, but three constraints make this fundamentally different from typical LLM deployments. So, one is the tail latency. So, our M1 queuing analysis show a phase transition where small load increases cause large tail latency spikes. The energy IoT budgets are radio dominated. Energy byte transmitted costs and energy. Sorry, every byte transmitted costs energy. The security here is RAG grounding improves factuality but creates an instruction injection channel that is particularly dangerous in IoT, where outputs can affect physical systems. So, what we study here is given n devices and operator queues, how should LLM capabilities be deployed to satisfy latency deadlines and energy budgets while controlling RAG security risks? So, that is what we study here. We compare four architectures spanning the design space. So A1 cloud chat GPT. So the simplest is the device upload raw logs to remote data center. So easy but worst latency and energy because here like every query requires a full round trip with raw data. A2 is Edge RAG plus LLM gateway, which moves retrieval and interference to local edge server, eliminating wide area round trip. But the gateway becomes a queuing bottleneck here as device count grows. A3 hybrid semantic compression. So the gateway converts raw telemetry into compact semantic artifacts, event summaries, statistical sketches. So like these both retrieval and interference. Dramatically, this reduces both uplink bytes and LLM context length. A4 on device a small LLM. Here, each device runs a quantized model for intent routing. Only compact but pre-processed summaries go upstream, uh, which minimizes the radio energy and privacy exposure. The compounding insight here is reducing bytes before the network and reducing tokens before the LLM multiplies, that gains the efficiency. Our stage-wise latency model decomposes end-to-end latency into 6 measurable components. The T-sense is telemetry collection, typically 5 to 10 milliseconds. Uh, T uplink depends on the payload size divided by effective bandwidth. So for cloud-centric A1, this grows with n as more raw data is uploaded. So the T gateway is the gateway processing modeled as M1 queuing. So this is the critical component. As arrival rate approaches service rate, latency rises into infinity, creating a phase transition. So here the retrieval RAG, the T retrieval and T ranking, these scale with K documents. So the T LLM scales with the total token count, and the T down is the response delivery. The gateway queuing component is the key. So it creates a sharp knee where adding just a few more devices can push the system from 50 milliseconds to 500 milliseconds latency. So this is why the capacity planning and the architecture choice matter so much here. Every per request combines the radio transition and compute. Radio energy is proportional to bytes transmitted. So compression directly reduces energy cost. The table here shows the compression cascade across architectures. A1 uploads 50 kilobytes of raw telemetry, expanding to 12,500 tokens in the LLM context, costing 48 millijoules per request. A4 uploads only 2 kilobytes of pre-extracted intent, yielding just 500 tokens and 14 millijoules, a 3.4x reduction in the energy. So here the key insight is that compression ratio Y reduces both the uplink bytes and context tokens proportionally. Since both radio energy and LLM interference cost scale with these quantities, the savings compound. This is why hybrid and on-device approaches are so effective. RAG improves the factual grounding but creates an instruction injection channel. Our three-layer guardrail provides practical defense. Layer 1 is the trust-aware RAG score documents using a weighted combination of relevance and trust. Trust considers source authority, digital signatures, and freshness. This prevents low provenance documents from dominating context. Layer 2 is the policy filtering strips instruction like patterns, redacts sensitive identifiers, and constraints tool actions to an approved whitelist. Layer 3 is budgeting caps which with the retrieval width of k and context token length. So this simultaneously bounds latency cost and attack surface. The risk model formalizes the trade-off. Risk rises with the document contributing to context and decreases with the guardrail effectiveness. The P95 latency scaling table reveals the critical differences between the architectures. The Cloud Chat GPT A1 hits the 150 milliseconds deadline at just 25 devices. At 50 devices, it reaches 320 milliseconds, more than double the budget. At 100 devices, it explodes to 1.2 seconds due to the queuing phase transition. Edge RAG, which is A2, is better but still crosses 150 milliseconds at around 30 to 35 devices. The gateway queuing bottleneck remains the same. Hybrid semantic compression, which is A3, stays within the budget up to 75 devices and reaches only 185 milliseconds at 100 devices, still manageable. On this device, the small LLM A4 is most scalable, staying under the 150 milliseconds. So the red line here marks the 150 millisecond interactive budget. Everything above it means the system feels unresponsible to operators.
Hello, ma'am. Gentle reminder to conclude your presentation in the next minute.
Okay, sure. So these numbers are interconnected, right? So the fewer bytes means less energy, less radio energy. The fewer tokens means faster interference, and both together keep the system within the latency budget. So here, the critical architecture principle is always separate LLM planning from physical actuation. And finally, the last slide. So the 4 takeaways here, right? So the first one is the ChatGPT fails at IoT scale. And the second one is compress before transmitting. Third one is guard your RAG pipeline with the trust scoring. And the last one would be separate LLM planning from physical actuation. Thank you. Happy to take questions.
Okay, ma'am. Can you just let me know how you handle the failure or the connectivity issue?
So for for the for this model with the RAG security or
Yes, ma'am, for your model.
so here basically I'm not sure in the perspective of the failure and connectivity, but what we have focused is here is to strengthen and guardrail the RAG so that we can achieve high security scoring.
Yeah, ma'am, can you just let me know what is the biggest bottleneck in adopting the LLM at the edge?
I think so here LLMs process on the weight-based transition of the data. So like once the data is injected in a high confidence manner, although the two other sources of data gives the accurate information, it still considers the high confidence data. So I think that would be the clear bottleneck in this perspective of the security.
Okay. Did you implement any mitigation strategy, ma'am?
I think there are like a lot of research that is going on with the multi-authentication score, like for example, signature scoring basis of the weights. So still trying to, but not 100% achieved with the mitigation of poisoning RAG.
Okay, ma'am.
Okay, sir, any questions? All right, thank you so much, ma'am.
Yeah, thank you. Thanks for your time, questions, and also like I appreciate allowing me to present.
Yes,
Thanks.
thank you so much. Now, next, I would like to call Nishu to present her study on Unibid College Student Marketplace platform.
So good morning, respected judges and everyone present here. Today, I'm going to present our project titled Unibit College Student Marketplace Platform. So this research is developed by our team under the guidance of our mentors. The aim of our research is to create a secure and structured marketplace specifically for college students. Wait, ma'am, am I audible?
Yes, ma'am, but we cannot see your screen.
Yeah. Now?
Yes, ma'am. We can see your PPT. Please continue.
Yeah. So, in today's digital era, online marketplaces like Amazon and Flipkart have transformed buying and selling. However, college students like us still rely on WhatsApp groups or word of mouth. This leads to problems like lack of trust, no proper tracking, and unorganized transactions. And to solve this, we developed Unibid, a secure student-only marketplace platform. And this is also our final year project. So I'm just reciting the problem statement. The current system has several issues: no proper authentication system, no structured product listing, uncontrolled transactions, no auction or donation system, as well as high risk of fraud and disputes. So our proposed solution is Unibid, a platform where only verified student can buy, sell, donate, or auction products in a secure and organized way. Like existing platform like Amazon and Flipkart are not student focused. Research mainly focuses on authentication, trust system, and payment integration. However, there is a gap. No dedicated campus based marketplace exists, and Unibid aims to fill all of this gap. So the system architecture we we have used the architecture. Like the first one is presentation layer that is made of Java Swing UI, application layer, business logic using core Java, and data layer. We have used MongoDB base for the same. So the module overview is like our system consists of four main modules. First one is user module, handles registration, login, and profiles. Then we have product module that allows listing, editing, and view products. And we have then transaction module that manages buying, selling, auction, and donation. And then we have admin module, basically controls users, product, and transaction. The technology stack that we are using is for the front end, we have used Java Swing. For the back end, we have used core Java with object-oriented programming and multi-threading. And for the third one, that is database, we have used MongoDB for scalability and fast operation. Our database design is like users, product, and transaction. Its schemas less and structure allows flexibility and supports real-time updates. Uh, we have implemented strong security features as well, like unique student authentication, role-based access control, data validation like mobile number and price checks, secure transaction with stamps and logs. Our system was successfully implemented. All modules are working properly. We achieved secure login, efficient product management, and real-time transaction. And the limitations are basically we have desktop based application, limited security features, like no online payment integration. We are working on it, and environment. The conclusion is Unibit successfully solves student trading problems by providing a structured and secure platform. It also demonstrates concepts like object oriented programming, database integration, and real time system design. So these are the references, and thank you for your attention. Like, I would be happy to answer any question.
Shikha ma'am, any questions?
Yes, ma'am. तो और fill कर दीजिए. Yes, ma'am. Sir, ma'am, can you just let me know what technology you are used over here for the front end, back end, and the database?
Ma'am, can you repeat the question?
What technology you have used here in for front end, back end, and for the databases?
Yes, ma'am. Like for this project, we have used Java-based technologies. Like we all are working for in Java only. So on the front end, we use Java Swing to design the user interface, and for the back end, we have used Core Java to handle business logic and application functionality. Additionally, for the database, we used MongoDB, which is a NoSQL database to store and manage user and product data. And we also followed OOP, object-oriented programming principles, and implemented the architecture to keep the system modular and maintainable.
And did you conduct any user testing or the feedback analysis?
As of now, ma'am, like yes, we have like we performed basic usability testing for our system. Like we are college students, so we asked a group of students in our college only to use the application for common tasks like listing a product, searching items, and participating in auctions. And based on their interaction, we observed how easy the system is actually to use. and for like we are thinking to scale the project as well.
Okay. Thank you, ma'am.
All right, thank you so much, ma'am, for your presentation.
Thank you, ma'am.
Now, this is the last call for K. Surya Teja.
Madam, good
Or
morning,
any-
madam. I'm here, madam. I'm here, madam.
Yes, sir. Please present your study on adaptive hybrid rhyme optimization for reliable feature selection and photovoltaic MPPT in dynamic conditions.
My screen visible, madam?
Yes, sir.
My
We
screen
can see
visible,
your Zoom
madam?
screen.
Okay, madam. Thank you. So my topic on adaptive hybrid design optimization, reliable feature selection, and photovoltaic MPPT in dynamic conditions. So here my presentation overview, different technical terms and motivation, research problem, and work done so far. And these are the different definitions we talk about, like that is how where we are getting maximum power
Sir, your
extraction.
voice is too low.
And
I'm
there
not
is a
able
PV
to hear
like
you.
light into electricity. So global max.
Sir, your voice is too low. I'm not able to hear you.
Madam, please wait, madam. Please wait, madam. Hello, madam. Hello, madam.
Yes, sir.
Yes, sir. Yes, sir.
Is it audible, madam?
Yes.
Shikha ma'am, are you able to see his
Okay.
presentation? Surya sir, we are not able to see your PPT screen.
No.
We can see your Zoom screen right now.
We are not able to see his
Madam.
presentation.
Okay, madam. Okay. Madam, age visible, madam. Is it visible,
Sir,
madam?
we are able to see your Zoom screen. The Zoom screen, not the PPT.
Okay. Now, madam. Now, madam.
We can see a light pink screen. I'm not sure if this is the presentation.
No, sir, actually your PPT is not visible to us.
Okay, sir.
Ma'am, can you ask other candidate to present us, to give his presentation?
Madam, now visible, madam.
Yes, ma'am. Surya sir, please share your online recording of the PPT and presentation to us. Is that all right?
No, okay. Just wait.
Yes. Lastly, Nabila
Madam, my
Kausar.
screen is visible, madam.
Yes, sir.
My screen visible, madam.
No, sir, we cannot see your PPT. I request you to please share your presentation to us. Till then, I will call out to our last presenter, Nabila Kausar. Ma'am or any of the co-authors, are you here with us?
Ma'am, may I remaining?
Yes, ma'am. Who was it?
Gauri Sayam.
Yes, hello. Okay.
Madam, madam,
Yes, sir, please give me a minute. Gauri ma'am, are you able to share your screen now?
Okay.
Madam?
Sir, please wait a minute. Another presenter will be presenting now. I will call your name after this. Yes, Gauri ma'am, please present your paper on AI-driven health risk advisor, a predictive approach to personalized healthcare. Gauri ma'am, you are on mute, ma'am.
Okay, sorry. Good
Yes, sir.
morning. Good afternoon, everyone. I'm Gauri Sayam, and today I am presenting my work on AI-driven health risk advisor, a predictive approach to personalized healthcare. This project focus on preventive healthcare, which is very important today because instead of treating disease lateral, we can predict and prevent them early. The main idea is not just predicting, but also helping user takes the right action. Now, this is my outlines. Abstract, introduction, problem statement, literature survey, research objective, proposed methodology, system architecture, ethics and privacy, application, expected output, conclusion, and references. So, moving to forward, abstract. So basically, this project is based on real world problem. Non-communicable disease like heart disease and diabetes cause around 74 of global death, which is very serious. The issue is that these diseases are usually detected very late. So I develop an AI-based system that predict health risks and give personalized recommendation. It use model like random forest and exhibit and give accuracy of more than 90%. Also, it works like a basal virtual health assistant. Moving to the introduction, rapid increase in a lifestyle related disease worldwide. If we look at today lifestyle, disease are very increasingly rapidly. People often ignore early symptoms, don't go for regular checkups, have unhealthy habits. Also, health care access is limited in many rural areas. So instead of waiting for disease, we should focus on early prediction and prevention. AI help here because it can analyze large data, detect patterns, give quick prediction. So this project focus on predicting before symptoms appear. Now, literature survey. From previous research, logistic regression 85% accuracy, random forest 92% accuracy, ZZ boost accuracy 94 accuracy. Random forests work well because it combines multiple decision tree. XGBoots improve accuracy by reducing error step by step. But the problem is most system gives only yes or no output, no proper user interface, no recommendation system. So the gap is clear. We need a complete and user-friendly AI system. Now the problem statement. The main problem are later diagnostic lead to serve a complication, no real-time health monitoring system, lack of awareness in rural population, existing ML system only prediction. But in real life, prediction is not enough. If someone is at risk, they should also know what should I do next. So we can a system that provide prediction plus recommendation. Research objective. The objective of this project are build a model with high accuracy above 90%, provide personalized suggestion, create a simple and user friendly interface, improve health awareness, ensure data security and ethical uses. Also, personalize is important because every person has a different health condition. So now next, propose methodology. Now let's see how the system work. First step, data collection. We collect data like age, BMI, blood pressure, glucose, lifestyle habit. Second, data processing. We clean the data, handle the missing value using KNN, normalize value, remove error. Step 3, feature selection. We select important feature like age, cholesterol, glucose because not all data is useful. Fourth step is model training. We use logistic regression for the baseline. Random forest, XGBoost. These models learn pattern from past data. Now step 5, prediction. The system predict low, medium or high risks. Step 6, recommendation. This system gives suggestion like diet plans, exercise routine, using rule and NLP. So suggestion are meaningful. So all over it works like a smart health advisor. Now next, system architecture. This system follows simple flow. User enter data, backend process it. ML model predict risks. System shows result plus recommendation. The front end handle user interaction and backend handle logic. This make system scalable and flexible. Now come to ethics and privacy. Healthcare data is very sensitive. So I use the backend framework Python Django. So we ensure security authentication, data encryption, anonymization. We also focus on fairness, reducing bias, and transparency. Because wrong prediction can affect real lives, we also consider standard like GDPR. Next, application, personal health monitoring system. This system can be used in personal health monitoring, integration with wearable device, hospital and clinics, corporate wellness program, government health planning. So it work at both individual level and large scale. Next, expected outcomes. We expected accuracy above 90%, F1 score above 0.85, ROC AUC above 0.90. Also, real-time prediction, personalized health advice, impact around 40% lifestyle improvement, 20 to 30% reduction in disease risks. So the system create real-world impact. Now, moving to the conclusion, AI can transfer healthcare from reactive to proactive. This system predict early, provide guidance, is simple to use. It is especially useful in rural areas. Future scope, multi-disease prediction, mobile application and cloud deployment. Thank you. Happy to open to answer.
Shika ma'am, any questions?
Yes, ma'am. Ma'am, how do you handle the patient data privacy and compliance with the healthcare regulation?
Ma'am, using KNN immutation.
Ma'am, data privacy I'm talking about.
Data privacy by the email and password and we use a Django framework that already having authentication system. So these are authenticate and
Okay, ma'am. What are the risks if the model predict the wrong, incorrect prediction and provide the incorrect prediction? What are the risks?
What are the risks? Actually, ma'am, incorrect data. This is AI, and they are also provide not accurate data, so we can connect the doctor.
I'm not. What you're saying, I'm not getting your answer.
Mm. Please pardon me question.
I'm just asking, what are you saying? I'm not getting a proper answer.
Okay. Can I ask what was the question?
Question? What was the question? How does your model? I'm asking, what are the risks if the model provide incorrect prediction?
Oh, sorry. Incorrect prediction. Um, we use the data sets on the Kaggle, like diabetes and heart CSV. Uh, from these, the system will predict the disease.
Okay. Okay, ma'am. Thank you.
Thank you.
Yes, thank you, ma'am. K.
Madam,
Surya, sir, can you please try to share
madam,
your PPT one last time?
okay. Is it visible, madam?
Yes, sir. Yes, sir.
Madam, my topic is adaptive hybrid RAM optimization for reliable feature selections and photovoltaic MPPT in dynamic conditions. So these are my presentation overviews, like a definition of different technical terms, motivation, why I'm going this topic, and research problems, organs over different references. These are the definitions we come across, like mainly MPPT, maximum power point tracking, that is how maximum power extraction under varying conditions. So then PV, which converts sun into electricity. Global power maximum power point, which is highest power found in the PV curve, and local maximum power point, because this local maximum power point is normally due to partial shading conditions. So on these are the different classical methods: perturb and observe, particle swarm optimization, and meta-heuristic method like artificial intelligence. Now, mainly why I'm going for this topic is because there is a climate change concerns across the world. Like already recently, government updated the NDC schedule, NDC targets, like increasing renewable energy. Here we are using solar energy because solar is abundantly available in India because of tropical country. And there is a partial shading impact, like PV efficiency is drastically decreased to 10 to 20%. So that is one problem. And challenges with the conventional MPPT techniques, like it will project multiple power peaks under partial shading conditions. There is need for advanced MPPT algorithm to ensure higher accuracy, better tracking speed, and economical viability. So the research problem occurs is that the existing MPPTs has low tracking accuracy and steady state oscillations. Under partial shading conditions also, it will not project GMPP, like global maximum power point. And there is a hybrid method like meta-heuristic method, which requires high computational power, making them costly and complex to implement. So my adaptive hybrid MPPT methods need fine-tuning to balance computational efficiency and tracking speed. So there is a research objective like to enhance tracking accuracy and to develop efficient MPPT strategy and to reduce computational complexity which occur in fuzzy logic controls, and to design and to design hybrid and to design to reduce computational complexity, and to design adaptive hybrid MPPT framework that effectively balances tracking speed and computational efficiency, to explore integrate emerging technologies like AI and ML and quantum inspired optimization techniques to achieve faster convergence and improve the tracking speed and enhance the robustness in photovoltaic MPPT systems. So there is a work done, like I'm taking one paper like HSU et al. In 2023, which uses a rhyme optimization algorithm. So this rhyme optimization algorithm features certain global exploration capability. That means it explores globally and convergence at very fast speed. And in order to enhance future selection tasks and maximum power point tracking for a photovoltaic system under partial shading conditions, this study presents a hybrid rhyme optimization technique. So by including tent mapping into agent selection stage and piecewise linear chotic mapping to build sequence that optimize the algorithm parameters to achieve good balance between local exploitation and global exploration. So here I am using a hybrid rhyme. So apart from hybrid RAM, I'm using adaptive hybrid RAM. So to increase the convergence speed and to maximize the computational power with efficiency. So this is the model of PV diagram, and these are the equations. So under different conditions, like under different irradiation condition, under different temperature condition, we are getting maximum current and with voltage and power at the at maximum irradiation condition, like 1 kilowatt per meter square. So here in the second diagram, we are getting maximum voltage and current at 25 degrees centigrade. That is at the temperature of 25 degrees centigrade. So here we are using two figures, like we are using uniform condition. That means sunlight intensity is throughout the panels is uniform under different shading conditions, like partial shading conditions due to trees, buildings, and dust. Building shadings or dust. Because of these, there is a partial shading conditions occurs on the panels. So here we are getting different maximum peaks at the at different irradiation conditions, like P2, P3, P4. But under uniform irradiation condition, we are getting maximum power point, that is P1. So RIME optimization algorithm, RIME ICE is mainly we are using bio-inspired method like RIME optimization. RIME ICE is resulted from accumulation of water vapor in the air that has not condensed. It freezes and sticks to object. So that means the normal soft, we are using soft frame and hard frame. In soft frame, the ice particles will spread uniformly and depends on the wind speed. So, but in case of hard frame, it will concentrate on the only particular direction. Like here, I'm showing like ABC triangle. Here under the soft frame, like figure A soft frame, the direction of the wind is not uniform, not in particular direction. So it will be oscillating, and particles also not concentrated in particular direction. But in case of hard frame, the particles are at the bud points of T1, T2, T3. And RIME optimization algorithm, soft frame and hard frame. Here in soft frame, particle condensation randomly enlarge agent attachment area. So the agent won't grow indefinitely and stabilize due to environmental factors. So particle outside the escape radius fail to condense. But in case of hard frame, the diverge hard frame will agents accumulate in a particular direction. So this will favorable growth increases the functioning probability between agents. So this is the mathematical model. And in case of hybrid RIME, I am using both tent mapping with my RIME technique. So in case of tent mapping, it is nothing but the exploration is more consistent coverage of RIME search area. So that's why we are using tent mapping. So these are the zodiac sequence phases. And piecewise mapping means the uniform distribution used by RIME to produce random numbers can cause values to be uneven and impact the capability of global searching. So algorithm unpredictability and transversal features are enhanced by using choice theory. So like we are using random particles like R1, R2, R3, and these are the parameters, and these are the zodiac mapping equations. So adaptive inertia weight, why I am going to adaptive inertia weight means it has greater exploration possibility, and the convergence speed also very less. So that's why I'm using adaptive inertia weight in my technique. So adaptive cosine exponential function inertia weight is presented, which utilizes, so this adaptive weight is taken from the PSO. So particular particles from optimization technique. So by combining the exponential function dynamic adjustment mechanism with the oscillating features of cosine, the algorithm total concept is greatly enhanced through iterative process. So this is the methodology I'm using. By starting, we are getting maximum global power point tracking. So initialization of RIME with tent mapping, that is, it will explore globally. In each particle, fitness is computed, and at random, the best global fitness value is chosen. So generation of zodiac sequence using piecewise mapping. So using inertia weight, we are updating the formula, like we are updating the formula and then updating the population using stepwise soft frame search strategy. So fitness the equation and apply hard RIME puncture technique. So then to keep good solution and get rid of bad ones, we are using positive greedy selection methods. So by updating the population using stepwise soft frame strategy, we are getting tunnel criteria, like if a possibility is not get, that is, it will go again to the inertia weight, then inertia weight will be updated, then again this whole process will begin. So after maximum iterations, if get maximum power, it will be sharp. So this is the PV diagram, and I am using these parameters specifications like cell per module is 60. So by using these parameters, I am getting like in my AH time, like adaptive hybrid RAM, I'm getting steady state power of 174 watts with the efficiency of 99.42%. So
Excuse me.
showing that the maximum power will be getting from apart from other.
Hello. A reminder to conclude your presentation in the next
madam.
minute.
Okay, ma'am. Thank you. So there is a simulation outcomes of different algorithms under partial shading conditions. So here in part of an observed method, we are getting only 90 steady state power with efficiency of 51.42. But in the hybrid adaptive hybrid time, I'm getting nearly 170 steady state power with a double efficiency of 99.42. So from that, I'm conclude that the proposed adaptive hybrid time demonstrates significant improvement in addressing the challenges of MPPT in photovoltaic systems, particularly under partial shading conditions and dynamic operating conditions. So here we are getting partial shading conditions, we are getting maximum efficiency by using this method. By integrating 10 map strategy into agent selection stage, the method effectively balances both exploration and exploitation. That means the convergence speed will be very less in case of hybrid time optimization technique. So beyond MPPT, the hybrid algorithm also proves efficient in feature selection. And with the comparative analysis, the AH time method is better suitable method. So these are my references. Thank you, madam.
Shikha ma'am, any questions?
Can I ask some question?
Yes, sir.
Yeah. Sorry, I will ask about the result of the comparison of between optimization. Yeah, I saw in your presentation is you get data with the different load.
Sir,
Do you have data with the same load?
sir, please, sir, please once again repeat, sir.
Last two slide, because I saw the highest load is with the best efficiency.
Yes, sir. Yes, sir. Yes, sir. With my technique AH time, we are getting the highest efficiency, sir.
With the last two slide, I think this compression. Slide 25.
Yes, sir.
Yes, that's right. Yes, the watt. This I saw the watt is high. The highest watt load is highest the efficiency. Do you have the same watt? And then why you did you take data with the different load? What's your
Sir, actually, I'm taking these parameters. So from these parameters in simulation, I'm getting these results, sir. In adaptive hybrid time, I'm getting 99.42% of efficiency, sir.
Because I'm wondering if you use the same load, the PSO will be higher
Yes, sir. Yes, sir.
efficiency also. Yes.
Yes, sir. Yes, sir. These bio-inspired method like PSO and getting less efficiency, sir, because of under partial shading conditions, the convergence is low, and so for that, that's why the maximum power will not getting, sir, because global maximum power point tracking is difficult to identify in partial shading particles from optimization techniques, sir.
All right. Shikha ma'am, any questions?
Yes, ma'am. How do you does your method avoid the local optima effectively, sir?
Maximum it will avoid, madam, but there is compared to other methods, it will avoid maximum. That means it will get global maximum power point at a very low with less time with accuracy, madam.
Okay. Did you perform any ablation study to validate the feature importance?
And actually, I'm looking in that work, madam. Actually, I'm using quantum techniques based on this.
Okay, thank you.
Thank you.
All right, thank you so much, sir. Now, this is the last call for Nabila Kausar. Nabila Kausar or any of the co-authors of this paper. All right, we move on to the closing remarks. I sincerely thank our authors for their excellent presentations and contribution in the session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for the support during this 11th version and all the previous 10 versions of the conference. And we will be happy to have you in the 12th version in 2027. All the presenters would be getting their digital certificates through email within 2 working days, and the publication will be live within 7 to 8 months. Hence, kindly cooperate with the team of ICTIS 2026. I would like to thank our session chair, Professor Shikha Sharma, for chairing this session. I'm sharing a token of appreciation on behalf of Team ICTIS and Global Knowledge Research Foundation and partners. Thank you for your presence, ma'am, and please share any concluding remark.
Okay, thank you all. Thank you all the presenter for their excellence contribution. The session highlight the innovative work across the AI, healthcare, IoT, system design, reflecting the strong research depth and the practical relevance. I appreciate everyone's participation and wish you all to continue success in your research journey. Thank you.
Thank you, ma'am. I would also like to thank Srinivasulu Gogula sir for chairing this session. And with this, we conclude our session. I would request everyone to please turn on your cameras for a quick snapshot of the virtual conference. All right, thank you everyone. Have a great day ahead. Thank you.